And can you see my screen?
Yes, we can.
Okay. So today I'm going to talk about writing a new server with extended functions. For the previous tutorial Tom has done, he has given a very good introduction about how to do coding in OpenFOAM, and what he taught is quite it's a very good introduction, so people know a little bit like how we do it. So in this case, it will be a more specific application. First, I would like to give an introduction about what I'm going to talk about today. It's basically based on the Interform solver, which is the two-phase solver based on the VOF method, volume of fluid method. And I would like to add a temperature field for this solver. So in the second part, I will describe this Interform, and then I will do the tutorial about adding the temperature field to this solver step by step, including library modification, solver modification, and finally try to compile it. After the new solver, I need to test it, so I will set up a test case and validate this solver. Okay, so to start, we already know that OpenFOAM has a lot of native applications and is covering a very wide range, including multi-phase, single-phase, Euler Lagrangian, a lot, and even reaction flow. But for a lot of occasions, that the native code doesn't fit all the needs of the physical problems. Then in this scenario, that the user needs to do some modification based on the solver, which is very close to the user's need. So in this case, a good start is to find an existing solver which is very close or almost close to what you need, and then add your own functions to this solver. There's a very good starting point is to add a temperature field to the icoform. In the previous tutorial, Tom has also shown this, how to add the temperature to icoform. So it's a very simple one, but it's a very good starting point to understand the procedure. And in this one, we will again try to add temperature in the two-phase solver. This work is particularly inspired by Damiano and Q Ming. Both of them have done very good work to implement the temperature field in this Interform solver. So they have also some documentations, and if you are interested, you can read it through this link. And this will be the outcome of this tutorial. So I will use the Dambrick tutorial case and try to add the temperature field. So here you see that I put some probes near the bottom and the right wall. And as we see that I put this as a constant temperature boundary condition. So when the simulation is running, the temperature, the hot ball will heat up the internal fluid. Depending on it, if it's air or if it's water, the temperature rise will be different. So first, I will introduce this Interform solver. So this solver is located in multi-phase in OpenFOAM solver's multi-phase Interform. And if we look at the interform.c file, we can get a description about what this solver does. So this solver basically solves for two incompressible isothermal immiscible fluids using a volume of fluid based interface camping approach with optional mesh motion mesh topology change, including adaptive remeshing. The governing equations is the continuity equations. I will bring up this later. It's the continuity equation and the momentum equation. And also, since we need to solve the alpha, it's a phase fraction. So there is another transport equation for alpha. And the density and the viscosity is volume averaged. So we have the density rho equals to alpha 1 times rho 1 plus alpha 2 times rho 2, and alpha 1 times plus alpha 2 equals to unit 1. And this is the same for viscosity. For those of you who don't know too much about multi-phase flow, you can run the OpenFOAM inbuilt tutorial in this location, just execute.outrun. So you'll get the dam break animation. Yes, so since we need to modify the solver, we first need to understand the structures and the files and even the codes of Interform. So in this case, we will go into this Interform directory and say and look at the files inside this one. So on the right, I have a snapshot of this all the files. So it contains a lot of header files and this interform.c, the main code file. In this one, the most relevant one is like pressure equation, the velocity, the U equation, and create fields to create all the necessary fields needed for this solver. One thing to notice is about in this OpenFOAM version 7 structure, there is in the same level, in one level upper Interform, there is a directory called VOF. And inside this VOF directory, it contains a lot of alpha and set delta headers. And these are needed by Interform because because a lot of solvers are using this VOF method. So in this file structure, OpenFOAM just put all the relevant header files relevant to VOF in this VOF directory. But it's later on when we do the modification, we need to copy this to the Interform, but we will show that later. Okay, now I want to go to the terminal. Okay, so the first thing I would like to show is, so if I go to the here, I would like highly to recommend one IDE is the Visual Studio Code. So you can, if you don't have it, you can use sudo apt install code, I guess, to install that one. So in this case, it will install this Visual Studio Code. It's a very good IDE. So here I will show some advantage of this one. So in this OpenFOAM folder, you can use the form for the alias to go into this OpenFOAM folder and just use this code to call the Visual Studio IDE. I maybe close this one. Close all. Yes. So now we go applications, solvers, multi-phase, and Interform. So first we go to the interform.c file. In this one, you have the description here, and you have a lot of declaration files before the main function starts. One thing I want to point out is this immiscible incompressible two-phase mixture.h, because you will see this later on. And after when the main function starts, first it will include some basic header files like set root case list and quit times and create dynamic FV mesh. Until this one, we include the until this one, line 60, we include create fields.h. So now I want to jump into this create fields.h. So I will just right click and go to definitions. This is a very good advantage of using this Visual Studio IDE because it's tried to connect the code and then you don't need to jump here and there using the Vim or gedit. But to enable this feature, you need to install this C++ extensions. So yeah, if you don't have this one included, it will not read all this C++ language features, and it will not do this dynamic linking automatically. But if you do install that extension, it will have this feature. Okay, so now I go to create fields. So you see here that I'm reading the create fields just right in this Interform directory here. So the first thing is to include r delta t.h, and after that it creates the prgh field and the velocity field, and create the flags reading transport properties. Here we see that we have an object called mixture, which is constructed by the velocity and the flux field. And this object belongs to this immiscible incompressible two-phase mixture class. And after that, for example, the alpha field is initialized by this object by calling a function called .alpha1. And this is the same for the density ρ1, ρ2. It's not directly defined here, but defined in this object function. And this object belongs to immiscible, incompressible two-phase mixture. And this one is declared in these header files. So that's sort of the connection between the header files and how we use that to do some field or object initialization or create fields. And after that, since we are using the VOF method, we need to calculate the mixture rho, the mixture density. So we create a volume scalar field, and this is the IO object. It will read if present, and it is initialized at alpha1 times ρ1 plus alpha2 times ρ2, which is the principle of the volume WOF method. And after that, there is some kind of flags definition. And in this one is in the incompressible two-phase flow, the pressure, what we are solving is more like a static pressure. So it's the PRGH. And after that, we need to get the real pressure field. And the real pressure field equals to the PRGH plus the ρGH. It's like the dynamic pressure plus the static pressure. So it's the total pressure. Okay, so that's what create field is doing. So I go back to this interform.c and continues with after line 60, after create fields. So after that, it creates some alpha flags and includes the initial correct flags and etc. And when the time starts, so it will read some controls and set delta t, set current number, and then run into the pinball loop. So this is in the pimple loop. We first need to solve the alpha equation, and then we solve the velocity equation, and then solve the pressure equation, and do this in a pimple loop. Okay, so I'll go back to the presentation. So this is one way to effectively say how to read the code with taking advantage of Visual Studio Code. Another one has already demonstrated by Tom. So it's using the online C++ source code guide. I put the link here. So if I go that website, so it's cpp.openfoam.org, and depending on which version you are using, you have different extension here. So now I'm using version 7. In this one, I'm interested in this immiscible incompatible two-phase mixture. So I can just search this class in this search box and get a description about what it does. And also, it's very good to get the inheritance here, because here we can see that this immiscible incompressible two-phase mixture is inherited from incompressible two-phase mixture. This inherited is important because when you define or try to add a new field, you need to locate where you put this field in. So you need to know if I need to put it in this class or this class. So it's always good to know the inheritance and know the dependency structure and put the code right in the right place. And if I click this one, you will see that this incompressible two-phase mixture is also a child class, or is inherited from 3 parent class: IO dictionary, transport model, two-phase mixture. And like what we saw in the left tab, this immiscible one is inherited from this one. So it can help you to understand some structure of OpenFOAM. Also here, in this incompressible two-phase mixture, you have some variables, and you can sort of get an overview of which variable is from which class. And what if you want to do it with Visual Studio? So here, let's also take this immiscible incompressible two-phase mixture, because we are going to change this later on. So now if I also do a right click and go to definitions, so here you can see that it will jump into the SRC folder. Yeah, we can just maybe look at here. So it's under SRC, transport models, immiscible two-phase mixture, etc. And in this few lines, you see that this immiscible incompressible two-phase mixture is inherited. Yeah, sorry, it's here. It's inherited from 2 class incompressible two-phase mixture and interface properties. And now if I want to see the definition of this incompressible two-phase mixture, I right click and go to definition. So it will jump into this one, and you see the inheritance similar as what we saw on the website. So it's inherited from 3 other classes. Okay. Next is to look at the make folder. In the make folder, we mainly have 2 files. So one is files and one is options. On the right, I list what's list the content in these two files. So in the files, it basically specifies the solver name of which which source file this one is going to compile, and after the compilation, which executable is called, the name of the executable and the location of this executable. In the options, it tells the location, the include path of all the header files, and in this exe_libs is all the relevant library needed for this solver. For a more detailed description about this make files and make options, we can check the user guide. I also put the link here. It should jump to the website. Oh no. Yes. So it's in chapter 3.2, compiling applications and libraries. So here you see kind of the philosophy of doing code or library compilation, and explains what the header files does and how to compile with wmake, and what's the functional make options and what's the functional make files. So this is very useful. And also OpenFOAM has a lot of preset environments, like for WM project directory, this will just directly go to the form directory. And if it's WM project user directory, so it's linking to the user directory. This is also useful when you compile a new solver, because a general rule is that when you compile a new solver or new library, you don't want to put it into the OpenFOAM default ones, because you have the risk to destroy the old one. So you always it's a best practice to always compile new applications or new libraries in your user directory. In this case, we can say the Interform in the make files in this exe equals form underscore app bin, which means the Interform will be compiled to the OpenFOAM application directory. And here in the make options, we have this lib underscore src. In this case, it also shows using an environment variable to point to the source directory of OpenFOAM. Okay, and I put this bit. So the next step is to tell you about how to do this solver implementation. So first, the governing equation in this red box is the default or this original Interform equations, and now we want to add this temperature equation to this one. So the temperature equation is very similar to the momentum equation, but yeah, it's rid of this one. It's this one, not like the Ecoform tutorial Tom showed before. This it will also consider this is the real temperature equation. It's not only like a passive scalar, because it also contains the specific heat and the thermal conductivity. In this case, since we are also using this volume of fluid method, this thermal conductivity is also volume averaged, and then the specific heat is total density averaged to keep the unit consistent. Now, like I mentioned before, when you try to add new variables, you need to understand the code and know where to put these variables. So in this case, like I explained before, this immiscible incompressible two-phase mixture library is important because it creates an object, and inside this class, it defines a lot of functions to return the relevant field. So here we can say that the rho, the density is written in this class. It's a bit complex to say this. And similar to this density, we want to put specific heat and conductivity. So next step is to find in which file we define the density. And in that file, we will add this K and Cp. So yes, here is what I explained both from Visual Studio Code and from the online website. This immiscible incompressible two-phase mixture is a subclass, is a child class of this incompressible two-phase mixture. So we jump into this incompressible two-phase mixture class and say that this is where we define this viscosity and this density. And in the same level, we should add K and Cp. So in this tells us that we need to modify two libraries. One is this incompressible two-phase mixture, and the other is this immiscible incompressible two-phase mixture. So next we will do this. For this tutorial, I have put a very thoroughly command sequence. So after the tutorial, or if you want to do it now, you can just copy and paste. It should work. I have tested. So now, yeah, let's do it side by side. So first is to change to your user directory and make a copy of the, so it's WM. So this WM project user folder will go back to your user form directory. In my case, it's Minghao -7. And in this case, since I already have implemented this one, so I just move my old SRC file to something, yeah, the original one, let's say, and do this command. So make the SRC file and go into this one. So copy the original transport property, transport model folder into here and change transport models here. Yes, so now we copy the OpenFOAM source code transport models into our user directory. And what we are going to change is this incompressible two-phase mixture. So I'll give it a new name called my incompressible two-fix mixture. Oh, it doesn't work with. Yeah, it works. Okay, it's in the incompressible directory. And change the name of it. And go into this my temperature incompressible two-fix mixture folder, and also change the name for the .h and .c file. It's always good to keep the directory name the same as the code file name. So this is for the .c file, and then for the .h file. And also, if we go into the code, we will see that it's still called the incompressible one without the new name. So it's also good to do a replace and change everything to the new name. So in this, I use this seed to do a global replacement and find the incompressible two-fix mixture and change it to my temperature incompressible two-fix mixture. So now we have done the case of file preparation. So next is to add all these thermal data like K and CP in your own designed incompressible two-fix mixture code. So I also use Visual Studio Code to open this. So in the .h file is the declaration file. So in this one, we see that the density is declared as dimension scalar, row 1, row 2. So after that, maybe I can bring this one is a little bit larger. So first, we need to change the .h file for the declaration. And after the density, we need to add all these ones. It's the K1, K2, and the specific heat CP1 and CP2. So I'm not going to do it here, but I can show you what the complete files. And after that, it's after that, we go into this member function section. In this member function section, we also imitate what row 1 and row 2 is written. So it's just adds the K1, K2, and CP1, CP2 to return, return a constant access to these two properties. So it's very similar to row 1, row 2. What you can do is just to copy this one and paste it and change the name of the function to, let's say, K1, and then the returned variable is K1 underscore. And the same for K2 and CP1, CP2. And further below, we have we have other functions. So after new f, right before the correct function, we also need to have this K effective and CP effective. This is to where we need to, we will define it in the .c file. So the K effective will be alpha1 times K1 plus alpha2 times K2. And then the CP effective will be the density average, the effective specific heat. But in the .h file, similar and the other declarations, we need to declare this function. So in the .c file, we can define it. So we just add it here after the new f and before the correct function. Oh, yes. So move to the .c file. Here we also mimic what row 1, row 2 is written. So row 1, row 2 is written as this. And after that, we declare, we put how row K1, K2, and CP1 and CP2 is. I don't like this, but it's too small screen. So K1 is the first is the name and then the dimension and then where to find it. And the same for K2, CP1, and CP2. This dim energy, dim time is some predefined unit in OpenFOAM. You can check it. Then in the member function, in the .h file, we have declared this K if, and then the CP if. And here in the .c file, this is how it is defined. So K if equals to alpha1 times 1 plus alpha2 times K2. And this is CP as written in the equation as shown before. So next is to, after the modification, we then need to compile this one. But before compilation, we need to do the modifications on the make directory. So the make directory, like I explained before, you need to change the name. I go back. I think it's maybe good to just show the files that I modified, because I realize this is not very clear to do this step by step online. So I'll go to the one I have prepared, the transport properties, and then the incompressible, and my temperature incompressible to fixed mixture. So one level up, so let's do it like this. So you see this, my temperature incompressible to fixed mixture is under this incompressible directory. And this incompressible directory has a make folder. And what we need to do is change the files and options in this make folder. So before, this was incompressible to fixed mixture and then incompressible to fixed mixture.c. But since you have changed the name, so you also need to change the name in the make file to make it consistent with the new name. And in the options, you don't need to change anything because this one, it doesn't, because you have already copied the transport models, the whole directory to your user directory. So in this one, you will just do a wclean and then wmake libso. So with this modified code, and I can open a terminal from here in Visual Studio, and just go to this incompressible. Here you see this is what I modified before, my temperature incompressible two-phase mixture. So I do a wclean and then wmake libso. So you see that it's trying to compile for every file you specified you written in this make files. Another thing to point out is that here, before it was form libbean, which is the default OpenFOAM library where the default OpenFOAM library stores. But like I said before, it's a common practice to put your modified library to your user directory. So you change from form libbean to form user libbean. It should compile quite fast. Okay, so I go back to the presentation. So next step is to modify the immiscible incompressible two-phase mixture, because this is the child class of this incompressible two-phase mixture. It's like we first modify the parent class, and now we want to modify the child class. This one is quite straightforward because if we go into that, okay, now if we look at the completion, now it says it's success with not any error. And you see here, the compiled library is stored in this home Minghao OpenFOAM Minghao 7 platform. So it's not stored in the OpenFOAM platform because you specified this form user lib. So it doesn't destroy the original library. Yes. Go back to the Interform code. We say that this immiscible incompressible two-phase mixture is just a child class of this incompressible two-phase mixture. And we have already modified this incompressible two-phase mixture to add the conductivity and the specific heat variable and change the name. So in that case, we also need to modify this one because you already modified the parent name to my temperature incompressible. So in that case, you need to change the name inside this immiscible incompressible class as well. And what this class is doing is just to call some functions. If you look at the .h file, yeah. So there is no specific things to change in this one because in the .h and the .c file is quite clean in this one. There is no new variables defined here. It's just some links to the old to some other libraries and call the functions in that library. And in the .c file, it's even simpler to just only have the constructor and the member function. So in this case, what we really need to change is just change the name of the incompressible two-phase mixture to the new name and to what you have modified. Yes. So if we can quickly go through the command. So first we change the name of this immiscible class to myTemperature immiscible, and then go into this myTemperature immiscible, and like what we did before, rename it to myTemperature immiscible, and then do a search and replace. And this is what what we need to change for the .h and .c file. And after that, we need to change the make folder directory, including the file and the options. And here, the main change is also the name of the source file and the path from form lib to form user lib bin. And in the make options, since we compile the old one incompressible transport model to a new library name, we also need to replace the old name with the new name. And to include the form user lib bin, I also add this -l and to include the path, or like this is to tell where to find the libraries. By default, it will search for form lib bin, but since you compile the new library to your form user lib bin, so you need to include this file in make options to for the library to be searched. So again, let's look at the modified version. So here I have my temperature incompressible here, and in this .h and .c file, basically we just replaced the old name with the new name. And in the, you see here, my temperature incompressible two-phase mixture. And in the make file, in the make files, we changed the name and the location or the destination of where this library will be compiled to form user lib, and the name of the library to my temperature incompressible two-phase mixture. And in the option file, it's the name of the parent library incompressible transport models, and the path to find this user compiled library. Yeah, again, we can compile this one with wmake. So I go into this my temperature immiscible folder and then do wclean and then wmake libso. So it will compile a new library, and here again it is in the user platform location. Yes. So to summarize, I know it's maybe a little bit confusing, but it's actually quite straightforward after you understand some basic knowledge, understand the structure, or understand the general rule, do a new library or do a new server, you will realize this is quite straightforward. So to summarize, the general step is first you make a copy of the existing library and then rename it and then modify the source code according to what you need. And after the source code modification, you also change the corresponding make files and make options to be sure that you are compiling the new library, and you have all the relevant paths and libraries along with it, and then compile with wmake. So until now, we have done the library modification. It's mainly the incompressible two-phase mixture and the immiscible one, and both of them, or these two, has been modified to my temperature incompressible and then my temperature immiscible. Yeah, this is the directory change, and also the library. Since we compiled these two library, the library name has also been modified from lib incompressible to lib my temperature incompressible transform model, and lib immiscible to lib my temperature immiscible. So next is to modify the Interform solver. Yes. So yeah, I think maybe I forgot to mention that why I need to do that. If we go back to look at the Interform make folder, in the options we will see that we will need this. Where is it? Incompressible. Am I looking? Oh, sorry. It's here. So in this Interform make options, we will need this immiscible incompressible two-phase mixture library. So that's why the first step is to go directly to modify the library first before you really modify the solver. Yeah. So the library modification is done, and then now we need to modify the solver. The step is similar. First, you also want to compile this new solver in your user directory. So go to your user directory and make some directory called solvers, and then copy the original. I think I forgot -r here to copy it recursively. To copy the original Interform to this folder, and then rename it and change the name, or replace the old name with your new name. So in this case, I call it my temperature Interform, and also change the make files and make files, including the name of the code and the location is from the default OpenFOAM application bin to form user application bin. So by doing so, yeah, let's go to the code. It solves my temperature Interform. Okay, so by doing all these steps, you actually just finish the rename. So if you just compile it, nothing will happen, but a new solver called my temperature Interform will be generated, but it's performing the identical functionality as Interform, because you haven't changed any source code and also the libraries. You are still linking to the old library. So the next step is to change the code to include the temperature equation, and then to update the linked libraries to your modified one. Yes, so here first, what we need to use to do is to modify the code in the create fields. Yes, so let's say, because previously you are using this immiscible incompressible two-phase mixture as a declaration for this create fields. For this mixture object, but now you modify the library and call it my temperature immiscible. So this is the first thing you need to do is to replace the old library with your new library. And this is what it does with this seed command. Yes, and also to imitate what row 1 and row 2 is written, you put K1, K2, CP1, CP2 here as well. For any modifications, I have this addition starts and addition ends. So after the tutorial, you can download the source code and try to read it in details. Next is, since we need to solve the temperature field, we need to create this row CP field and the row CP5 for the flux, and also the conductivity. Here is, we also try to mimic what row is written here, because row CP is like row times CP. So it's a very similar scalar field as row. And this is how it is written. And here we see that in the initial, when we try to initialize this field, it's row times mixture, and then the function you defined in the library. And this is also the same for the conductivity. Next, I think I'm running out of time, but I have some slides. I'll go through it quickly. In the alpha equation, we also need to add this row CP5 because we need to calculate for the temperature equation. And in the alpha sub equation, try just imitate what row is written to add row CP. And for the T equation, this is what the T equation looks like. So it's very similar to the momentum equation. So if you look at the U equation, you will realize a lot of similarity. So in this case, you just put the something like this. So the FVM DDT rho CP, comma T corresponding to this one, and the second term corresponds to this one. This Laplacian K, comma T corresponds to this term. The reason why I add this one, I have a comment here. This is for better convergence, because the first time when and also in some other tutorial case, they don't have this line. But I realized that if I don't have this one, when I do the tutorial case, the temperature tend to diverge. And I got this idea is from this interface change form. They added it to increase the convergence. And when the solution converge, you will realize that by adding this source term, and if the solution converges, this will be the continuity equation, and it will be 0. So it doesn't affect the solution, but increase the convergence. Then in the main code, my temperature interform.c, like similar as the icoform, what we saw in the previous tutorial with Tom, you just include this T equation after the pimple loop. And what just another thing to remember is that you also need to change the header file name from the old immiscible one to my temperature immiscible one. And with all these things done, the next step is to modify the make directory, and to here is the new one. This is the old one. You can see that the old one links has the line inclusion. Try to find it in the library's SRC directory, but you compile your transport models in your user directory. So this is the difference. You need to include this, change these ones to your newly compiled directory, and also the library name. Before it's just immiscible one, and now you have this my temperature immiscible one, and also the path to find the library. Yes, so that's all we need, and then we do wclean and wmake, and then you can get the new solver. And to this is all here. This one is to show that if I do the which, let's say my temperature interform, you see the returned path is in your user directory. But if you do the default interform, it's in the OpenFOAM directory. Okay, so the next, I'll go this very quick. It's the my temperature dam break case. Before we run this new solver, we need to modify a little bit on this tutorial case. So first, I copy from the tutorial case dam break and rename it, and then because we need to solve the temperature, so we need to add the boundary condition for temperature. So it's very similar to pressure. You can copy pressure and modify it to something like this. In this one, I applied a fixed temperature and the right wall and the lower wall with uniform 300 Kelvin, and the internal field, the initial value is 270. So the right and lower wall will be the hot wall, and it will try to heat up the internal fluid. Also, we need to add this mod Cp and K in the constant transport properties, so it can read this value and do the calculation. And in the system FA scheme and solutions, we need to add the scheme for the temperature, and then also the solver needed for solving temperature. You can always find some reference type solver and reference FA scheme to use in other tutorial files. And in the all-run script, I just extend the end time to a little bit longer, and also change the application name from the old one to my solver. The reason why I want to extend the end time is that I want to see a much clear temperature rise. And then you just execute this all-run script, and then use Interform to see the result. And here is what we say. On the right contour is the temperature. So we say the temperature on the right wall, and then the bottom wall is the hot wall with 300 Kelvin, and the internal field is 270. And when the water comes here, we say that if the probe is located in the bottom and it's covered by water, so the temperature rise is much less than the temperature rise if it is exposed in the air. This is because the water specific heat is much larger, or at least 2 or 3 times larger than the air. So it's the delta temperature will be smaller. So this is quite reasonable. Okay, so to summarize, today we went through the Interform solver and just dive into the code and look at some important libraries. And next, I described it step by step by command to show how to add the temperature field to Interform, including the library and solver modifications. And then we test or verify this solver, the functionality with this dampbrick, this modified dampbrick case. And just please to note that there are a lot of other ways to do this code modification. I don't think I did it in a very efficient way, but I think it's very easy to understand. Maybe not very user friendly for the beginners, but if you start to try to program in OpenFOAM, this is a very good practice.